thanks to IPAM and the organizers for this wonderful meeting. And thanks to Matt for collaborating with me on this. It's been a lot of fun. So what is this subject? We're trying to invent a subject, and we haven't yet. And that's actually good for the audience, because all I'm going to tell you about is some examples, and then you guys can invent the subject and get all the credit. So the idea is...
How long did you work on trying to do that?
Trying to invent this subject? Well, it's been... we're busy people. We're stuck in between corporate constraints and so on, so we probably only spent a few hundred hours. So linear algebra is something very elementary. You learn it in undergraduate school or high school. And there are sort of two versions. One is just vector spaces over a field. And then, maybe you also want to include the inner product and talk about inner product spaces. That'll sort of be my point of view. So unitarity and things like that are natural. So I consider that package, freshman course. And it has two very prominent generalizations in mathematics. One is topology. If you add parameters to linear algebra, you get the theory of bundles. Because what is a bundle but a vector space parameterized over a base, often a manifold? And what is a bundle map? It's just a linear map between vector spaces, also with a parameter x, x being a point in the manifold. So here we have all the famous developments from the 1960s and on, K-theory, characteristic classes. Then sort of there's an orthogonal generalization of linear algebra when you put tensor structures on the vector spaces. So you have a vector space, and part of it is controlled by Allison, and some part is controlled by Bob and Claire. And that's sort of the science of quantum information. And our thought was, as mathematicians, we like the push-out diagram. Shouldn't there be a theory that has both tensor products and parameters? Now, actually, this was anticipated to some extent in the 1960s, because K-theory does have a multiplicative structure, and that's the tensor product on bundles. But people never really thought about the entanglement aspects of sections or vectors that took place in these tensor product bundles. So I'd say that development came up through this leg, and we want to look at this leg of the interferometer. Okay.
I have a question.
Yeah.
As a physicist, the left-hand side, it's not just the multilinear or tensor product structure which is important. I mean, it's one part of it, but the other important part is Born's rule, probability.
Absolutely, yep.
So how does that go over into the other side you're building on now? Are you guys going to talk about that?
Well, I wasn't going to talk about probability, but I don't think that Born's rule is particularly tied to tensor product structures. It makes perfectly good sense in any Hilbert space. So I guess, though I'd be very interested in it, probabilistic and entropic discussions, maybe we can get into it at the end, it's not really the structure of the talk. What I'm doing is I'm trying to combine parameters with tensor. And now you can have a push-out diagram that goes out there that combines Born's rule. And then we'll have a vertex of the cube up here, and we can have a talk next year on that.
Okay.
Okay, so I want to remind the audience, since some people are not topologists, of what a bundle is. So this is my slide on topology, what a bundle is. So let's just work up in the most elementary way. The simplest bundle that's not a product that you'll ever see is the Mobius band, which is an interval bundle over a circle. And I've just drawn here, metaphorically, the boundary of that interval bundle. So it looks like a two-point fiber over the circle. And this already contains what's important about a bundle, is it's kind of trying to be a product. You have a base and a fiber, but it's not quite, because as you move around the base, the fiber is really sort of a torsor. It doesn't know its coordinates, and the coordinates can be transformed after you go around a loop on the base. In this case, an essential loop, but you can also transform coordinates gradually by like following a connection in differential geometry or in potential in physics, and you can have interesting bundle structure even locally. It's not interesting topologically, but it's interesting geometrically. That's what curvature is. So there's no curvature in this Mobius band example, but now down here there is. So this is sort of the next bundle moving up in dimension. This bundle was over the 1 circle, S1. This bundle, the 1 sphere, this is over the 2 sphere. It's the Hopf bundle. Physicists know it as the unit, the total space. If I look at the unit vectors in here, I see the states in C2, the normalized states in C2, and then this would be the block sphere. And the ambiguity, the fiber ambiguity, is the phase, which is being divided out. So all these bundles, I'm writing them as fibers with vector spaces, but often I'll think about the sphere bundle as well, the unit vectors in there. And this bundle is characterized by a Chern class 1, which, and if you think of it as a real bundle, a real two-plane bundle, forgetting the complex structure, it has Euler class 1. And this Hopf bundle I want to use today as a warm-up for the bundle that I'll be spending my time with, which in physics is called an instanton, an SU2 instanton. I don't think it has a name in math. And this is the straightforward generalization of the Hopf bundle, replacing the complex numbers by the quaternions. So the base, instead of being the compactified complex plane, is the compactified quaternions, S4. And the fiber, instead of being 1 copy of C, is 2 copies of C. I put the little j in there to suggest that its direct sum is the quaternions. And the relationship is, if you think of clutching functions, bundles over a sphere can be very easily understood by mapping the equator of the sphere involved to the structure group. And the structure group in the case of the Mobius band is the 2-point group, and multiplication by the non-trivial element is what creates this twist in the Mobius band. Here, the equator is a circle, and the structure group is U1, and the degree 1 map is what's giving you C1 equals 1. That's the degree of that map. And here we have the analogous thing. The equator is the 3 sphere, and the structure group for this is the unit quaternions, also SU2. And since the 3 sphere is diffeomorphic to SU2, there's a degree 1 map, just like there was from the circle to U1 here. And that degree 1 map is producing this instanton, which, I first learned about it from Donaldson theory, that this is like the bubbling of energy off in the Yang-Mills theory.
So nobody used the other one?
Oh, going up in dimension?
Yeah, the S8.
Yeah, no, this is all good too, but this is just to talk about examples, and I'm restricting to the simplest examples that illustrate the points. And I'll be spending time with this just because when the fiber is one-dimensional, we can't talk well about entanglement. We need to have a fiber of which admits a non-trivial tensor decomposition. Okay, now for this audience, I don't need this slide. This slide is the comparable slide to introduce bundles. This is supposed to introduce an entanglement. But I still think there's a moral point that I want to make, which is that when you look at tensor products of linear spaces, so if there is a tensor structure, then they look really different to you when you're like standing at the origin and looking out. The main thing about the vector space, if it's naked and has no additional structure, is that every direction is the same. But if there's a tensor structure, then some directions are simple. They're just tensor products of a vector from each factor, written either of these two ways, and some are sums of such things, which are necessarily then entangled. That's what it means to be entangled, is just not to be simple. And my icon for simplicity is a quadric, because this is a quadratic equation that has to be satisfied for vectors to be simple. So it's some complex code, in this case, in the lowest dimension, complex codimension 1 variety, giving you the directions which are simple. And it's this inhomogeneity that is the focus of quantum information and will be our focus as well. Okay, so what's the motivation for combining these two subjects? So one is the Brion zone, or the momentum torus. So you could imagine that you have a physical system which is periodic, and it's then very natural to study it as a bundle over the momentum torus. So the periodic system may, within a unit cell, still have many degrees of freedom. There may be, different atoms or ions inside the unit cell and electrons, and each of these will have some perhaps small Hilbert space describing its degrees of freedom. And the entire Hamiltonian over the periodic system can be either viewed directly in some infinite dimensional context, or it can be viewed via the Fourier transform with respect to lattice translations, and thought of as a bundle of finite dimensional systems over the Brion zone. And this point of view is exploited brilliantly by Kitaev in his classification of free fermions, and actually made explicit in a paper of Matt's where he used the torus trick to consider, when Kitaev considered Rn, he considered Tn, the torus. So if you have tensor product degrees of freedom in the fundamental domain, you'll see naturally in condensed matter physics bundles whose fibers have tensor decompositions, natural tensor decompositions. And then if you have sections of these bundles or mapped between these bundles, it's then natural to talk about the entanglement property in a family way, because you want to know what entanglement a section has, for example, over each point of the Brion zone, and it might vary. Another motivation might be experimental parameters. If you're studying a quantum mechanical system in the lab, then labs are full of all these machines and computers and things, and I've walked through these labs and there are dials, and you might turn these dials, they get thrown out of the lab. But that's an example of a parameter space. The base of the quantum mechanical system is the settings of all these dials. And it may be that these are not like boring parameters, that may not be a contractible space, even though it looks like it. Turning a dial looks contractible. It may be that the physics is only up to some kind of gauge equivalence. It may be that if you increase the flux through the sample, every integer amount of flux returns you to the same or similar physics. So you can have interesting bases by varying experimental parameters. And I think also there are applications, potential motivations or applications in high energy quantum gravity, and we can discuss that at the end if anyone likes. Okay, so let me give the first and simplest example. So let's just take 2 copies of the instanton bundle and tensor them together. So this is a bundle now with fiber C4, as thought of as C2 tensor C2. And it's natural to break it up into its antisymmetric and symmetric parts. And the antisymmetric part is one-dimensional, spanned by the singlet. So that has a very natural section, which is just up, down, minus, down, up. That's a trivial bundle, one-dimensional. And now we're left over with this 3 complex dimensional bundle, the symmetric part. And the question is, what can we say about sections of this bundle? Well, first thing to say is there will be non-zero sections. By the way, every time I say section, a section is just a cross-section of the bundle, I'm going to assume that it's a non-zero section, because I'm interested in its entanglement properties, and the zero vector can't really be discussed in that context. So the first thing is by dimensional analysis, there will be non-zero sections because this is 3 complex, hence 6 real dimensions. And since the fiber dimension is more than the base, a generic map won't hit the 0 section.
When you say never zero, it means
Never vanishing.
never one.
Non-vanishing, I think, is the math term. This is more plebeian. Now, so I want to say, and the next slide will be about what we can say about the entanglement properties of these sections that surely exist by general position. And the first comment is already on this side, and that is that the entanglement of a section at every point makes sense. So before we talk about the concept, we should make sure that it's sensible. And why is that? The study of entanglement is the study of states modulo local operations. You're allowed to do anything you want on local factors. That should not change the amount or the type of entanglement under discussion by definition. And when you look at a vector space that you're not holding directly in your hand, but you only know up to automorphisms of tensor factors, you still have all the information you need to discuss entanglement in that vector space, because it's precisely the ambiguity that comes from the unknown automorphisms of the factors that is ignored in the subject of entanglement. So it's perfectly sensible to talk about the entanglement of a section, even though we don't have coordinates exactly on the space. We understand the tensor composition, but we don't have coordinates on the factors, but that's fine for talking about entanglement. Okay, so the first little fact, non-trivial fact, is that the section of this section S of the symmetric square cannot be simple at all points. So in other words, we can't have an unentangled section, meaning a section that's unentangled everywhere. So rank 1 would be another way of saying that. No plus signs in that previous formula. I'm using simple and rank 1 and unentangled as synonyms. So why is this? Well, if we had a if we had a section of the symmetric bundle, then of course it can be written this way. That's because it's symmetric. And we could just take one of the factors and think we're done, because why don't we just ignore the second factor and look at the first tensor factor and say, oh, okay, that's a section of a non-trivial bundle, that's a contradiction. But the little difficulty with that argument, the reason it's not quite correct, is that when you have a tensor product of 2 vectors, the scalars move freely through. So this expression does not really specify at every point in A. So the best you can extract from this is a projective section. So it's a section whose fiber is not C2, but whose fiber is CP1, the lines. So, but we can repair this little glitch immediately, because there's a line bundle. I haven't drawn it here, but there's a line bundle in the problem which exactly encodes the obstruction to removing that phase ambiguity. The ambiguity of this A hat, to try to remove the hat and turn it back into an A, that ambiguity is this unknown phase. But line bundles are associated with a Chern class. The obstruction to lifting A hat to a true section is in H upper 2 of the 4 sphere with coefficients in Z, but there's no second homology there, so we can easily resolve. So this shows that in my first example, let me just go back to the example. In this example, no section can be rank 1. Well, but there's a stronger statement. In fact, it must be that for some point on the 4 sphere, this section is maximally entangled. So let's prove this. Let's assume that the entanglement entropy does not reach a maximum, does not reach the maximum possible value at any point on the sphere. Then in particular, it's not maximally entangled at the South Pole. So we write the section at the South Pole out in some coordinates. I mean, this is not too important. It's just that theta is not taking an extreme value. In other words, I should have written this as a condition, but the absolute value of cosine theta and sine theta, if they're equal, that's maximally entangled. So theta is some angle other than 45 degrees or its multiples. It's odd multiples. So in order to study this problem, let's again projectivize and look at oh, sorry, do I have a typo? Sorry, this should be a 2. CP2 is the projective space of the symmetric power. The symmetric power is 3 complex dimensional, taking its projective space. That's a CP2. So that's, I think later on, all the CP2s are correct. So these are the projective triplets. And the unentangled ones, the rank 1s, because it's a quadratic condition, are the degree 2 curve in CP2. And it turns out that this degree 2 curve is a topological 2-sphere. I mean, it's a smoothly embedded 2-sphere in CP2. Topologists learned this picture. In CP2, this is CP1. It's just a line in CP1. And that's the degree 1 curve. And if the degree 2 curve is just 2 lines, but that's a singular example, but they can be resolved to be 1 line. And if you want to know what the degree 3 curve is, you can keep drawing another line, and you resolve. Each of these resolutions is like a local connected sum. So the first one is 2 spheres get connected sum together, you still have a sphere. If you have 3 spheres crossing cyclically, when you resolve, you get an elliptic curve. You get topologically the torus. But anyway, degree 2 is, degree 2 by this picture is a 2-sphere. And remember, that's the unentangled, or the rank 1 vectors. And now what we want to do is we want to understand, in addition to the unentangled vectors, we want to understand the opposite extreme, the maximally entangled vectors. So these are the ones that have maximal entanglement entropy, and they can be expressed as a general vector in the Bloch sphere, tensor itself, plus some phase times prime for perp, or the antipode on the Bloch sphere, which is the perp in C2. So this is a general expression for the maximally entangled, where U is a unit complex number, so the coefficients have equal norm. That's what makes it maximally entangled. And a little analysis of this formula shows that the maximally entangled vectors up to phase, because we're in projective space, is actually a copy of RP2. So it's the Bloch sphere with antipodal points identified. Basic reason for identifying antipodal points is you get the same state whether you have a prime here, or a perp here, or a perp there. Now it turns out, with a little analysis, that the region between unentangled and maximally entangled is actually a product of some 3D lens space with the interval. It's this lens space, which has fundamental group Z4, cross an open interval. So the picture of CP2, if you want to, I should say, this is kind of a cool picture. Everyone knows what happens if you remove CP1 from CP2. This is just the cell structure. This is equal to the 4-disk. But I had never seen, until Matt and I had this question, what happens when you remove the degree 2 curve instead of the degree 1 sphere. And this is homotopy equivalent to RP2. And the actual picture is there's a two-sphere here, which is the minimally entangled stuff. That's the C2. And then there's an RP2 here, which is the maximally entangled stuff. And then what's in between is foliated by these three-dimensional leaves. And it's a product, which are all these lens spaces. So this is a picture that we could get for any irreducible representation if we knew enough. But I'm sure experts in algebraic geometry can do all these things, but we did this by hand.
So Mike, if you project onto S4, is that picture a very simple one?
This picture?
The second one. We know CP2 covered S4. If I just project down, what do I get this?
You're saying there's you're talking about a branch covering?
Yeah, branch cover S4.
Under complex conjugation?
Yeah.
Yeah, I don't know.
Should be
Good
very
question.
simple.
It might be very simple. That's a good question. So, but this picture gives us the following diagram. Maybe I should back up to this diagram. So we have a not less than maximally entangled S of x0, but remember this force sphere has this bundle over it. So a bundle can always be trivialized over the northern hemisphere of the sphere. You can push the bundleness down just near the South Pole. So if you think about this section as you approach the South Pole, you can really understand it as the value of this section at the South Pole, but seen in different coordinates. And the different coordinates are this pi3 of S2. You look at, as you proceed in all possible three directions from the North Pole to the South Pole, the limiting value for the section appears in the coordinates of the northern hemisphere as the orbit of whatever the section was here under SU2. So this orbit, 2 slides ahead, is this three-sphere mapping into a neighborhood of the unentangled vectors. Changing the coordinates doesn't change the amount of entanglement. So you'll never hit max. If we didn't hit max at x0, we won't hit max under those changes of coordinates. But a large neighborhood of C2 is the same thing as just deleting max, deleting the projective plane. That's that product structure I indicated. But by elementary topology, this map that takes the action of SU3 into this neighborhood, this topologically is just the Hopf map. This is a neighborhood of the two-sphere, and the conjugation, or the action of S3, this is the map from S3 to the Bloch sphere. So this is the non-zero element of pi3 of S2, and it cannot factor the northern hemisphere, the extension of the section over the northern hemisphere cannot possibly factor into this neighborhood, because that would contract the non-trivial map into essentially the two-sphere. The map into the two-sphere is essential. In order to contract it, you have to leave this neighborhood. Leaving this neighborhood means some point in D4 must go through max. So at that point, it's maximally entangled. So in topology, we call such a diagram a compression. The outer square is kind of obviously there. And when you look at the diagonal, you're asking, it's written dotted instead of solid because it's a question. Can you compress the map? Is there a map homotopically there making the diagram commute? The answer is no. And that's how we prove that the entanglement must be maximal at some point. Okay, so let me move on to Claire. We've had Alice and Bob. Now we're going to have 3 factors. To get something interesting, I regard bipartite entanglement as a little bit old school. So multipartite entanglement is an incredibly tricky subject, and I don't think anyone knows a really good way of thinking about it. But one bit of progress was made in this lovely paper of Dur, Vidal, Sirac, where they introduced stochastic local operations in classical communication. And that means sort of what it sounds like. The stochastic means that you're happy in this equivalence relation, even if you only have a 1% chance or anything very small of converting some states to other states. That's the stochastic, and then of course local operations, you can act locally on the factors and you can chat back and forth classically. Well, if you work through that operational definition into linear algebra math, it turns out it has an extremely simple form, which is that a state in the threefold tensor. Now I'm going to an example. I'm taking the threefold tensor product of just the simplest thing, a qubit, and we'll have another state, and we say that this state is, well, less than the original state or equal to the original state if these matrices are invertible. So the point is, you say that, let's say equal first. You say that this prime state is equivalent to this unprime state if there are three invertible matrices, so that 2 by 2 matrices, so that when acting on the tensor factors, it turns this vector into this vector. And you say that they're not equal, but there's an inequality in this partial order if you just drop the invertibility requirement. So like one of these matrices might be singular. Now, when I saw this definition, I thought something was wrong because I wanted these matrices to either be unitary or Hermitian, or I wanted the authors to be talking about quantum channels in some other space, and it just didn't seem right that there could be any statement just about matrices acting on the space themselves. And I called up Matt and said, Matt, what's going on? This seems crazy. And he said, oh, it's the stochastic part. It's the fact that you don't actually have to convert states, but only get a non-zero probability that makes this equivalence so simple to express. And that's in fact correct. So what they do in this paper, the main thing they do is they work out the answer for the partial order under this relation, in this case, C2 cubed. And you get 6 equivalence classes with the smaller ones at the bottom and the larger ones at the top, and the arrows are the partial order. So this ABC just means it's rank 1. It's A tensor B tensor C, no plus signs. This line here means it's A tensor an arbitrary state between B and C that can have any entanglement, and similarly. So then there are 2 interesting cases that are sort of fully entangling between the 3, and each are exemplified by a famous state that physicists had thought about earlier, the GHZ state and the W state, and they represent different classes. And it turns out that the GHZ is open dense. That's the biggest possibility. And this is a little cartoon, but I found it extremely helpful. It's a picture of these states in CP7. So CP7 is a picture of the whole partial order. CP7 is C8, which is the dimension of the tensor factor, tensor product, projectivized. So this picture is drawn in CP7, and the 8 points, which you see here as vertices of a cube, the cube is the product of 3 zero spheres, and it represents in the mnemonic here, it represents the product of 3 block spheres. And that's exactly what you have projectively for the simple vectors in C2 cubed. And then if you look at opposite pairs of circles, there are 3 opposite pairs of circles. That exemplifies extending, like in the A-BC. It means that the BC thing doesn't have to be tensor factored. It's general. So what was a block sphere now becomes a CP2. So it jumps up in dimension. It goes, this thing had the 8 points is complex dimension 3. The next one's complex dimension 4 because of that jump. And then W turns out to be complex codimension 1. And then the GHZ is generic. So it's open dense, it's complex dimension 7. And it's important actually to understand what this little linking circle is. Remember the GHZ state, sorry, the W state has those two factors. Sorry, the GHZ state has two factors. Where did I put it? And when you go around this circle, the linking circle to W, these two factors adiabatically get swapped. So that's actually important to know. So this mnemonic, by the way, is really helpful if you want to calculate the cohomology or homotopy groups of various substrata in here, because otherwise you'll just make some goofy mistakes. It kind of keeps all the Meyer-Vittori sequences in order. Okay, so how did these guys, Vidal and his friends, how did they prove this? How did they, establish the classification? Well, they studied the reduced density matrices of the state, which are, by reducing one factor, you get a map from C4 to C4. And it turns out that it doesn't matter which of the three factors you reduce out. There's a symmetry. So I just reduced out A to get rho BC. So you get these matrices of rank 2. They're rank 2 for both the W and Z state. But the distinction is that for the GHZ state, there are two simple vectors in the image of the of rho. And in the W case, the image of rho contains a unique simple vector. Now, that sounds kind of goofy because algebraic geometry is going to tell us that there should be two vectors because, as I pointed out, the simple guys are a quadric, and we're asking for how many intersections are there of a line with a quadric and a projective line in a quadric, and the answer algebraically is 2. But you can have either two generic intersections or you can have a intersection that's tangent, so a double zero, just like the solution to the equation z squared equals 0 as opposed to z squared equals epsilon. So you should think of the W thing as a little bit degenerate. It's kind of like the two simple vectors collided. And that's sort of what makes it a different class. And that I'll come back to that fact. That'll be useful to us in a little bit later. Okay, so now let's ask the question about this threefold tensor product bundle. Let's ask our favorite questions. Could there be a simple section? Well, by now, you guys can probably come up with the proof yourself. It's just as before. There can't be a simple section because if it was, we could write it as a tensor factor of A, B, and C in the names for the section in each factor. And we could choose one of them, A, and we'd have a projective section, and there'd be no obstruction to lifting, just as before. So there's no simple section. Let's ask the opposite question. Could there be an all GHZ section? The answer here again is no. And the proof is, I think, extremely fun and short, so I'm going to show it to you. So assume that the image of the section S lies fully in GHZ. Well, the section is over a sphere, and the sphere is simply connected. And that means no loop in the sphere can, under the section, be transported to a loop that links the W strata. Because no loop can link anything, because the loop is sourced in the 4-sphere, and the 4-sphere is simply connected. So in the 4-sphere, we can fill in that loop by a map of a disk, and then we can push that map of a disk using the section into the stratified picture of CP7. And if the loop linked the W strata, then the disk would cross the strata, contradicting the fact that everything is supposed to go into GHZ. Okay, so the fact that no loop links the W strata remember I told you that linking the W strata has a dynamical interpretation. When you Matt wanted to think of this as some kind of pump. We haven't figured out how to call this a pump yet, but if you pump around W, you'll switch factors. But if you don't go around W, no loop will switch factors. And that means you can consistently define which is the first and which is the second term of the unique GHZ representation. It turns out that up to permutation of the factors, there's only one way to write GHZ vectors as GHZ. That's a little tensor analysis. So having a well-defined, quote, first term, S1, puts us back in the original situation because the first term is just three things tensored together, and we have already seen that that's contradicts the vanishing of the cohomology class. So that's the proof that there's no fully GHZ section. And again, these are just examples. So if you ask me almost any other question, I'll have to say the answer is we don't know. You know, we just have checked a few things just to see if there was like life in this game. Okay, so when I first heard a little bit about quantum information, you know, when I went to Microsoft in '97, one of the things that was sort of in the air is there was a paper by Aravind just making a provocative comment that GHZ looked a bit like the Borromean rings. So this is in a paper he wrote then. And the idea is that, well, this is the Borromean rings. It's three circles in three space. Actually, here's a little exercise you can try. I've drawn those as circles, kind of, but actually they have to be ellipses. So it's a theorem that you can't represent the Borromean rings with three round circles. So you might enjoy thinking about that. But anyway, it's totally irrelevant to what I'm about to say. So what I do want to say about the Borromean rings is they have this property that if you cut one, any one, it's symmetric, the other two fall apart. So it's like intrinsic triple linking without individual pairwise linking being present. By the way, a little personal story. When I applied to graduate school, I thought I would enhance my application by stating some of my feelings and thoughts about mathematics. And one of the things I conjectured was that the Borromean rings could not exist. I didn't know that example, and I just said, well, maybe we can prove that if a bunch of things are linked together, then there must be pairwise linking. When I got to graduate school, Ralph Fox took me aside and said, "Here's the Borromean rings." And actually, in New Jersey, the drinking age was 18. I was young, I was 18, and I could drink. And there was a beer they sold, Ballantine Ale, and it had the Borromean rings right on the can. So, you know, if I had been in New Jersey, I would have known. But but I told that to Ralph Fox, and he says, "Well, you know, you're too young to drink, so it's excused that you didn't know." Okay, so the Borromean rings have the property that if you cut one, the other two fall apart. And the analog of cut in quantum information is partial trace. If you partial trace one of the three partners out, you get this reduced density matrix for GHZ, which is completely classical. So there's no quantum entanglement left. So in a sense, if you cut or trace, whatever the analogy is, the system falls apart. Well, this was fun, and people wondered whether it meant anything. But I think we can add some meat to this old observation by sharpen the analogy, if you like, by supplying a functor. It's like, suppose years ago people had come to you and said, you know, manifolds behave a little bit like abelian groups in some ways, but they didn't mention homology. Then you'd come along and you say, oh, well, I think I know what they were talking about. There's a homology functor that takes you from manifolds to abelian groups, and some things, you know, there's some additivity relations and so on. Okay, so that's what I want to do here. Take any rank 2 TQFT. So rank 2 just means two simple objects. So for example, the Fibonacci theory is 1. And then we can look at the three manifold, which is the three sphere minus the Borromean rings. So it has, if you remove a neighborhood of the Borromean rings, it has three torus boundary components. And the three manifold, famously, this is what a TQFT does. 2 plus 1 dimensional TQFT, what it does is it takes the bulk three manifold and it turns it into a vector in the Hilbert space spanned by the boundary. But the Hilbert space spanned by the boundary is just 3 qubits in the case of a rank 2 theory. Each torus is a qubit. And the theorem, Matt and I noticed, is that the Borromean ring complement lies in GHZ. That is, the section here, not section, sorry, the state is entangled in that class. The proof, the key to proving this is to use this distinction between simple and non-simple roots of the reduced density matrix. That distinction, which was discovered in the Vidal-Chirac paper, is how this proof goes. And what makes the argument, the calculation doable, is the S in SLOC. So remember, S is the stochastic part, and that means that when you study questions of entanglement with respect to their classification, you can use any independent basis. It doesn't have to be an orthonormal basis. That's kind of the import of the S. And it turns out that the Borromean rings is really hard to analyze in an orthonormal basis, but it's sort of easy in a non-orthonormal basis. And the point here is that a non-orthonormal basis for this 8-dimensional Hilbert space is just the meridional and longitudinal fillings of the 3 rings. Each ring you could either fill by closing the meridian, in which case the ring just disappears, or you could do surgery on the longitude. And this projects you, if you look at the partition function of the resulting 3 manifolds for those 3 choices, that gives you 8 numbers, which are non-orthogonal coordinates on that C8. But the analysis it's perfectly fine to use this non-orthogonal basis. And what makes this basis easy is the value of the components in this basis are just the partition function of the 8 different closed 3 manifolds you get by these different Dane surgeries. And the possibilities are you get the 3-sphere back if you fill in all. If you fill in 2, you get S1 cross S2. If you fill in 1, you get the connected sum of S1 cross S2 with itself. And if you fill in all 3, this is a beautiful little exercise. Longitudinal surgery on all 3 components of the Borromean rings is the 3 torus. So all those manifolds you can just look up in like Zheng Han's book on TQFT, and you can see what their partition functions are. And that's enough then to write down a quadratic equation and show that if it was class W, the quantum dimension would be negative, something like that. You just solve some quadratic equation.
Do you think this will be stable if you take the motion group of the Borromean ring?
Oh, well, actually, that's my last slide, is the motion group. So just to put that particular construction in the context of the rest of the course, the family discussion, notice that there's a Z3 symmetry of the Borromean rings. Click, 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 right? So we can build an infinite dimensional bundle, actually, based on this symmetry, where we take the Borromean ring complement, cross it with call it S infinity. You can just think of it as a large sphere, odd dimensional sphere, and look at the diagonal action of S3. So if you just act diagonally on S infinity, you get the infinite dimensional lens space, L infinity 3. And when you act diagonally on this product, you get a bundle over this lens space whose fiber is the, on the boundary, it's the disjoint union of 3 tori. In the bulk, it would be the 3 manifold. But if you apply the functor fiber-wise, what you have is a bundle of 8-dimensional Hilbert spaces lying over the lens space and this is its total space. And what we just proved, or what we just saw, is that this section is all GHZ. So this is kind of counterpoint to the previous example, where we had a threefold tensor product fiber, and there was no section that was all GHZ. Here, the sort of canonical section associated with the symmetry is all GHZ, essentially for a trivial reason that the same thing is happening in each fiber. The section, of course, being the value of the partition function. So that's my quick tour through entanglement of sections, trying to unite parameter families and tensor structures, and I hope someone in the audience is able to make this into a theory instead of a set of examples. Thanks. Yeah.